In this video, we're going to see a lot of great examples of where compositions of functions appear in the topic of business. Okay, so we have a composition of functions. We're going to have to use the chain rule, so that's why it's called chain rule in business. Okay, so let's start with a simple example. Maybe you've been in a place like this. Let's say that we know advertising helps our sales. Okay, so we're going to say D is the dollar amount that we've spent on advertising. Then, if X is the number of items we sell, well, how many items we sell is going to depend on how much money we spent on the ads. So X is going to be a function of D. But usually we see X as our input, not our output, because usually X is the letter that we input into a function, let's say R of X, which is our classic total revenue, and this one is as a function of the number of items sold. Okay? So it turns out that not only does our total revenue depend on the number of items sold, but that depends on how much we spend on advertising. So really our total revenue depends on how much we spend on advertising. So if we're going to recast the function R in terms of the independent variable D, dollars spent on advertising, that's going to be a composition of functions. Alright, so for this example, I gave us a couple of things to work with here. Let's say our revenue function is 18 times X. Let's take a minute and interpret that. Let's say R of X is in dollars, X is in number of items. What does the number 18 mean there? That means the price of the item, right? Because revenue is per item price times number of items. So here what this means is that items sell for $18 each. That's the per item price. Okay, so that's a typical revenue function. But now let's say that the number of items we sell depends on advertising dollars in the following manner. It's equal to 0.5D plus 20. Can you interpret those numbers for me? Let's start with the 20. What does 20 mean? 20 is actually the y-intercept on that line, which is to say that if we spend $0 on advertising right here, we'll sell 20 items. But for each additional dollar that we spend on advertising, something happens to the X. It goes up, right? And so what does this 0.5 mean? That's the amount that we have to spend to get like one more thing. Or for instance, I mean, if we spend $2 more on advertising, then we're going to sell 21 things instead of 20 things. So this slope of the line indicates how much it costs in ad dollars for us to sell an additional item. Okay? So let's compose these two things and see what we get the output. So if we compose R of X with X of D, we get R of D, which is really R of X of D, and that's the total revenue as a function of the amount of money that we spend on ads. Okay, so that's just our revenue function, now seen not only dependent on our number of items sold, but actually dependent on how much we spend on ads. What if we wanted to take the derivative of that with respect to D? What would that interpret to? That would tell us the rate of change in our total revenue with respect to the amount of money that we spend on ads, or as I've written, it's how the total revenue would change when we spend $1 more on the ads. Remember how you can kind of interpret the derivative of is that if the X variable goes up by 1, what will happen to the Y variable? Okay, so if the X variable here is the input ad dollars, then if we spend the $1 more on ads, what's going to happen to our revenue? It'll probably go up by a little bit because the things we sold went up, and so we got more money. All right, so let's go into how to calculate this using the chain rule. Hopefully you guys remember what the chain rule is and that you practiced the chain rule video. And first of all, let's just go back to the composition of functions and see if we can write down a statement for R as a function of D. Alright, now I've given you the outside function, 18 times X. The inside function is 0.5D plus 20. Go ahead and compose those in the manner stated and tell me what a simplified version of R is in terms of the input variable D. Okay, so going back to the instructions, I just copy down the outside function. Wherever I see an X, I'll put parentheses, and I'm saving that parentheses. And instead of throwing in the X, I'm going to throw in what the X is. So I'm going to toss in this entire statement right here, and that's the composition. But don't stop there. If you see some places where you could easily simplify, be my guest, simplify it, because that will make the rest of the things easier. Okay, so 18 times 0.5 is 9, so that's really 9D, and 18 times 20, that's 360, so really we have 9D plus 360, right? And from there we can actually just take the derivative, but I will do it again using the chain rule as well. Okay, so what would the derivative be after we've just simplified this down and seen it in a polynomial form of D? Derivative, hopefully you understand, is 9, and that's dollar, wait a minute. Here, the number's 9. Hopefully everybody understands the derivative number's 9. But if you're in my class, you know I'm also going to ask for the units. So what are the units on this? It's going to be the y units over the x units. And R is in dollars. And D is in dollars. But you got to be careful because they're two different kinds of dollars. And that might happen to you when you're in a business. You have like dollars coming from here, dollars coming from there. So what this is this is $9 of revenue per dollar in advertising. Okay, so dollars per dollars, you may not want to cancel it out and just see the number 9. The units are that my rate of change is my total revenue increases by $9 in revenue per each single dollar that I spend on ads. Okay, we already pretty much have the answer, but we can go ahead and use the chain rule anyway, just to confirm. The chain rule will state to us that r prime of d is equal to the derivative of the outer function evaluated at the inner function multiplied by the derivative of the inner function, just like that. Okay, so let's go back over to this board here, and we'll write down what's the derivative of the outer function, derivative of the inner function. If r is equal to 18x, what's r prime? Just the number 18, good. If x is equal to that linear function right there, then what's x prime? 0.5, that's right. And now following those instructions along, you can see that r prime is just the number 18. Now usually I would pop open some parentheses and put in the inner function, but there's no x here. You see, it's just the number 18. There's no x. So in order to evaluate r prime at x, I just have to write the 18 because there's no x. Moving right along, I'm going to multiply that x prime, which is equal to 0.5, and sure enough, that's half of 18, so it gets me right back to the 9. So either way, I've determined that r prime is equal to 9. That's not so much a place where you actually need the chain rule, because you can see by simplifying the composition we did not need the chain rule, but it's more just a fun example of how compositions of functions occur in business. Okay, so now let's move on to a couple examples where you actually do definitely need the chain rule, and I'm going to take it back to the financial math part of pre-calculus. If you guys remember that, fondly or in any other way. Do you guys remember the compound interest? Let's study compound interest a little bit in more detail now that we know about derivatives. Let's say S, the future value of our account, is 1,500 times 1 plus 0.01 R divided by 12 to the 120. Do you remember seeing equations like this in previous videos of mine? We spent a long time on this, yeah. So I've actually put in some numbers here, but hopefully you recall that this is the familiar general compound interest equation. And what this represents is it's the future value of an account where I've invested $1,500. So here my principal is $1,500. That's what I put in the account to start. And that's going to compound. Let's see if you can figure it out. This is compounded in which way? Compounded yearly, monthly, quarterly? Monthly. It's compounded monthly because you see it's getting divided by 12 right there, right? And for how long was it left in the account? For how many years, let's say? Well, if it was compounded monthly, then the number of compounding periods appears up here, which is 120, but that's 120 months, which is 10 years. So it's for 10 years. Okay? So what this equation is telling us is it's the future value of a principal investment of $1,500 compounded monthly for 10 years at a given rate R, and that's the only variable left. So really I'm seeing this as a function of my future value dependent on what's the rate that I get, okay? Let's study this in a little bit more detail. What we're really going to want to do is find S prime of R. So before we actually find it, and we have to use the chain rule here, there's no getting out of that. I don't want to multiply this 120 times by itself, okay? But before we actually do it, what is S prime? Like how I interpreted what R prime was over here. What actually is this? Try to write down a sentence similar to that and see if you can interpret it, because really that's the main takeaway from this class, is being able to interpret derivatives. Okay, so this is a rate of change, and it describes how your future value will change when we increase our rate by 1%. That's how it goes. And notice here the R must be defined as an annual percentage rate in percent, because I'm multiplying it by 0.01 to turn it into a decimal inside the equation. So if this was 5%, I would put actually the number 5 there, and the 0.01 would turn that into a 0.05 for me. Okay? So this is how my future value will change when the rate R goes up by 1. In this case by 1%, because R is in percent. Just like spend $1 additional on ads. That's what the derivative does, because it's a rise over run. So if we consider the run to be 1, then the value of the rise, or the derivative right here, will interpret as the change in the Y. Okay, so how's my future value going to change? How will my investment over 10 years change if I get 1% better deal on the rate? That's what the derivative is going to tell us. All right, great. So that will make you appreciate it more. So let's go ahead and start finding it. What is the derivative? We have to use the chain rule for this, okay? So we're going to chain rule to find the S prime with respect to R. Now if you're comfortable with the chain rule, you can go ahead and just do it the visual way, where you pop down the exponent and do it out, and I won't tell you. I want to see if you can do it. Or if you're still in your beginnings and you'd like to see an inside and an outside function defined, we can go ahead and do that. So we'll take it slow here, and let's assume that there's an outside function and an inside function, where the outside function is equal to what, and the inside function is equal to what. Okay? Alright, so depending on where your practice is, you may or may not be filling out this chart. Again, you don't have to necessarily if you are comfortable with the fast way, but it will get you partial credit if you're getting a graded assessment from me and you didn't quite get the answer right. Let's say you forgot something. If you at least had all this stuff written out, I would consider more partial credit. Okay, so let's talk about what the outside-inside function is. Inside function is actually easier to start with, because inside function is usually what's inside parentheses. It's as simple as that. Or what's inside a radical if you have a square root. Okay? So what's inside parentheses here? This is what's inside parentheses. Alright, so I'm going to call that my inside function. And then what did I do to that? I multiplied it by 1,500 and I raised it to the 120. So that's my outside function. And if you compose those two things, sure enough, you would get the original statement of the function back. Okay, so in order to get to the S prime of R, we are going to need the F prime and the G prime. So if you're going this way, and really if you wanted to get the partial credit from this way, you would also definitely need to write down what is the derivative of each one of those functions. Okay? So what's the derivative of this? Well, that's a pretty big number. It's 1,500 times 120 times R to the 119. That's a power rule. And what's the derivative of the inside right there? That's actually a linear function, so its derivative is going to be the slope, which is the 0.01 divided by the 12. But notice I didn't put an R there because it's just the coefficient, because this is multiplied by R to the first power. Okay? Alright, and now what we're going to do is that S prime is going to be the outer function evaluated at the inner function multiplied by the derivative of the outer function evaluated at the inner function multiplied by the derivative of the inner function. Okay, so the f prime right there is 1500 times 120 times stuff to the 119. Remember, you don't want to put the r there. You want to reserve a set of parentheses, and then you're going to throw in the g right inside the parentheses just like that. Then you're going to times it by g prime, which is that ratio right there. And there you go. That's the long ways of your derivative. But you can see that there is some really convenient simplification that can happen. And I highly encourage you to pause right here and simplify before you try to evaluate at any given value of r. Because you're not going to want to have to times all these stuff together over and over again. What is 1500 times 120 times 0.01 divided by 12? All together now, that's 150. Okay, so you just put a 150 there, and then you have 1 plus 0.01 r over 12, that quantity to the 119. There, that's the derivative. Now let's evaluate the derivative at a couple spots, and then we can use our interpretation to get the meaning out of that. Let's say what happens if r is currently 5%, then s prime of 5 is what? Approximately, because you're going to need to round this. So why don't you go ahead and plug in the number r equals 5 right here and see what you get. Round that off to 2 decimal places. Then we'll interpret that value. Okay, so I got 246.03 to 2 decimal places. And now I'm going to take a minute to step back and appreciate that number, which is to say interpret it. What is 246.03? What is that supposed to mean? What that means is, the meaning is, if the rate increased from its current state at 5% to one more than that, which would be 6%, my future value would go up by 24603. That's what it means. Okay, so currently I'm at an account that's offering 5% APR compounded monthly, and remember this whole thing's over 10 years. That's where the 120 comes in. Okay, but if that rate, if I got the bank to just nudge them a little bit and increase my rate by 1%, what would happen to that entire nest egg at the end of 10 years is that I would have $246 more at 6% than I would have had at 5%. Okay, so let's see that number a couple more times, evaluate it, and we'll talk about it. I also did s prime of 1, and I got approximately 165.63. And then I got s prime of 10, and that was approximately 402.70. And what is all this mumbo jumbo over here trying to tell me? If I evaluate the derivative at r equals 1, it tells me if r changes from 1% to 2%, if r changes from 1% to 2%, my future value after waiting that 10 years would be 165.63 higher under the 2%. Okay? And what this one says, s prime of 10, is that if r changed from 10% instead, went to 11%, then my nest egg would have been worth $402.70 approximately more than what it was at 10%. And if you indeed go back and calculate the actual future values at 10% and at 11%, and if you take the difference, you will find the difference to be approximately the amount of the derivative. It's not going to be equal in the same way that a marginal quantity is only approximated by the derivative, not strictly equal to it, but you get the idea. And you see how easy it was for me to plug in all different values of r here, and I didn't have to go back and evaluate the future value equation at 2 different points and then take the difference in order to see those things. I was able to see those things relatively quickly. So it's pretty useful, right? Let's do one more. How about if I gave you an equation that described your weekly sales depending on the price that you set your item for sale at, okay? So maybe you could kind of see this as a demand type of equation, but we'll call it weekly sales equation, and the weekly sales depends on the price of the item. That makes sense. How many of these am I going to sell in a week? Well, it depends on how cheap they are. The cheaper you make it, the more people are going to want to buy it. And let's say that this is the equation that I have right here, where P is my price in dollars, and Y is the number of items sold per week. So P is the price in dollars, and Y is the number of items sold per week, which is also called the weekly sales. Okay, I like to interpret derivatives even before I calculate them because I think calculating them probably the more boring part for you. Interpreting them gives them the meaning, therefore hopefully giving you the motivation to want to compute them. So let's talk about it right now. What does y prime of p mean? What does it mean? What does it mean? Try to use the units. What are the units on it? Okay? Y prime of p is in what unit? And then try to write a sentence where you say y prime of p is what? Go ahead and just totally use your own words. You don't have to take my word for it because I want you to understand this and take it with you into real life. Tell real life I said hi. Okay, let's see. Units first. Units are always output unit over input unit, okay? Output unit, number sold per week. This one is the number sold. That's what's coming out, right? Price, that's what's going in. Price in dollars. So the y prime is it dollars per items? Or is it items per dollars? I don't want you to mess that up on the test. It's output over input. So number sold. So it's a number sold per dollar. And that makes sense for what we're talking about because we were saying the weekly sales depends on the price, right? So the derivative is going to be a change in the amount that gets sold per week per dollar increase in the price, okay? So then what did you fill in here for a sentence? Y prime is the change in the amount sold, so it's the change in the weekly sales when we, and this pattern's always the same for whatever you're doing, the derivative is the change in the y variable. Change in the y variable. When we increase the x variable by 1. So when we increase the price by $1. Okay? So that's the general theme. You've seen it in my other video on your intro to derivatives. It's always the derivative is the change in the y variable when we increase the x variable by 1. So as long as you've really written down what your x and y variables are, you should be able to interpret the derivative. Now we can appreciate what it is, so let's go ahead and calculate the actual derivative, and then maybe we'll evaluate it at a certain price point and see what that means, okay? So what's the y prime going to be? Now we've done this a lot of different times. I'm going to do it the fast way now, and I hope that you can get yourself up to speed on a function like this where you can just do it without saying explicitly what's the inside variable, what's the outside variable, okay? So you can see the inside variable. It's right there, inside the parentheses, right? And the outside stuff is this number, and then this stuff was at this power. Okay, so now I'm going to do the power rule with the constant multiple rule, which is that constant multiple just along for the ride. The power gets taken down, and then we leave that stuff alone right in there. So 2p plus 1. And what power did it get raised to when we did negative 2/5 minus another one? What did you get? Negative 7 over 5. Yes, be careful with that negative number taking away another one. So this is the actual statement of the derivative. You could probably simplify that a little bit to be the number negative 2,000 multiplied by the quantity 2p plus 1 to the negative 7/5. Okay? Alright, that seems fine to me, I think. No. Do you guys see anything wrong with what I did? Did I just do this on purpose? Just to check and make sure you remembered the chain rule? Sure, yeah, that's what I did. Where's my mistake, guys? If you've really been studying the chain rule hard at this point, you can see that I have made one key mistake. And I want you to find it and pause the video if you need to solve the riddle. Okay, here's where my mistake was. Remember how the chain rule goes? The chain rule goes derivative of the outside, so I brought it down, and then I left the inside alone, and I did that till power. I did so much stuff, I got tired, and I forgot to multiply by the derivative of the inside function, okay? So you have to multiply by the number 2. Why do I have to multiply by the number 2? Because 2 is the derivative of the inside function, okay? The derivative of 2p plus 1 is 2. Don't forget to do that. I have seen that so many times, and I hate taking off points for it, but that's your classic mistake right there, okay? So built into the video for you guys to see it. Hopefully you caught me, but if you didn't catch me just now, I hope at least you're listening and you saw that, because this is my number one top mistake. Inside a power rule like this, where the power was already hard, there's fractions, negative numbers, all that stuff, I got tired and I made a mistake. I forgot the derivative of the inside function is 2, so I have to times 2 at the end. Okay, I hope everybody learned a good lesson there. And then eventually what happens is that this part comes into negative 1,000, then I times it by 2, and that's why I get negative 2,000 times that quantity to the negative 7/5. Okay, that was fun. What does it mean? I'd like to ask that question again after I put some numbers to it. So at a price point of $20, I'll tell you that y prime of 20, if you plug in 20 into there, should get approximately negative 1104. And now I want you to tell me what that means, okay? And I'll leave this sentence up here while you're trying to interpret it. But what I mean is, can you form a sentence for me that now uses the numbers 20 and negative 11.04 and kind of describes what that number is to that number? This is a hint right here. Okay, so now I'm going to erase this, and hopefully you've paused it and taken a minute to write down a sentence that's similar to what I'm erasing right here, but incorporates these numbers. That's what I was looking for, okay? So what does it mean? It means the number of items sold per week, which is the y variable. So it always starts, the y variable will change by derivative amount. So we'll change, but it's negative, so I'm going to take the negative and write go down. That's what the negative means. We'll go down by about 11.04 y units, which is items, when we increase the x variable, which is the price from $20 to $21. Okay? So if you are actually in a business situation and you've modeled your weekly sales by observation, by data points, you found that when I have it at this price, this is how many sell in a given week. Then I'll tell you that if you're thinking about changing the price from $20 to $21, what's going to happen is you're going to approximately sell 11 less items per week. Okay? Now, whether that's good or bad for you also depends on your cost function in conjunction with your revenue function and totally your profit function. So we're not actually sure if this is a good idea or a bad idea. You see, it takes down the number of items we sell, but it does increase the per item price. What did that do to our revenue? What did that do to our profit? We will need to model those functions as well and form the whole picture. You're going to see that later in the class when we talk about optimization. For now, I just want you to practice interpreting individual derivatives so you can really appreciate how and why we're getting these numbers.